This is Richard Hammack's Calculus 1 course. We are in part 2 of the course on limits. Today, lecture 12 on infinite limits. Today's goal is to investigate limits of the form limit as x approaches c of f of x equals infinity. Not a finite number, but infinity. Infinity is not a number, so technically a limit such as this doesn't exist. However, we will make sense of that today. To motivate the discussion, imagine you have this function graphed here, and look at the x value c. F of c is not defined, but as x gets closer and closer to c, f of x gets bigger and bigger and bigger, without bound. F of x approaches infinity, we would say. And that happens whether x approaches c from the left, as indicated here, or if x approaches c from the right. F of x would get bigger and bigger and bigger. And the closer x is to c, the bigger and bigger f of x is, without bound. So we express this behavior by saying the limit as x approaches c of f of x equals infinity. Again, this limit doesn't exist, but by saying that it equals infinity, we are expressing exactly how it doesn't exist. For this next function, as x approaches c, again, f of x gets bigger and bigger without bound, but in the negative direction. And if x approaches c from the right, f of x would also get bigger and bigger and bigger in the negative direction, become a bigger and bigger negative number without bound. We would say that f of x is going to infinity as x approaches c, going to negative infinity as x approaches c. And we write that as the limit as x approaches c, f of x equals negative infinity. Now consider this function. As x approaches c from the left, f of x gets bigger and bigger and bigger in the positive direction. We have the limit as x approaches c from the left of f of x equals positive infinity. But if x approaches c from the right, look what happens to f of x. It goes down and down and down. It goes to negative infinity. So the limit as x approaches c from the right of f of x equals negative infinity. Because we're getting two different things, infinity and minus infinity, depending on whether x approaches c from the left or from the right, we would say that the plain old limit as x approaches c, f of x, does not exist. So the definitions for today are the limit as x approaches c, f of x equals infinity means that x approaching c forces f of x to approach infinity. And the limit as x approaches c of f of x equals negative infinity means x approaching c forces f of x to go to negative infinity. And you could put a plus or minus for a right-hand limit or a left-hand limit on either one of these c's, here and here. You can actually come up with much more precise definitions. These are very informal definitions that we have in the box. They're perfectly sufficient for a first semester of calculus. If you go on further in calculus, you'll come up with more precise definitions for limits that equal infinity or minus infinity. Whenever you have such a limit that equals infinity or minus infinity, you call that an infinite limit. So today's topic is infinite limits, limits of this form or this form. Let's look at some examples. Here's a function, and we'll work out these limits for this function. First of all, the limit as x approaches minus 3 from the left of f of x. Now here's minus 3, and you can see as x approaches minus 3 from the left, f of x goes to negative infinity. So we get negative infinity. The limit as x approaches negative 3 from the right of f of x. Here's x coming in to negative 3 from the right. And let's look at the corresponding f of x values. They're going straight down to negative infinity. So this limit equals negative infinity. Finally, the limit as x approaches minus 3 of f of x, neither from the right nor the left. In these two previous limits, the right-hand limit as x approaches negative 3 equals the left-hand limit. They're both equal to negative infinity. So we would say the plain old limit as x goes to minus 3 f of x equals minus infinity as well. The limit as x approaches 2 from the left. Let's see, here's 2. X goes to 2 from the left. F of x goes to positive infinity. So this limit equals positive infinity. But the limit as x approaches 2 from the right of f of x would be, according to the picture here, negative infinity. As x goes to 2 from the right, f of x goes down to negative infinity. So then when we look at the limit as x approaches 2 of f of x, well, depending on whether it approached 2 from the right or the left, we got different things, either infinity or negative infinity. So we'd have to say this limit does not exist. We've concentrated in this example with x approaching minus 3 and 2 because those are the kinds of limits that we're talking about today. But of course, we could also have something like limit as x approaches 0 of f of x. And you can see here that as x approaches 0, f of x is getting closer and closer to, it looks like negative 1/2. So negative 0.5. Now on these pictures, on this picture of this graph, I've drawn these dotted vertical lines at negative 3 and 2. There's special names for these lines. They're called vertical asymptotes. This first line, which is the line x equals minus 3, is called a vertical asymptote of this function, f of x. It's a line that the function gets closer and closer to as x gets closer to, as the graph gets closer and closer to, as x gets closer and closer to minus 3. And simultaneously, the f of x values go to negative infinity. This so-called vertical asymptote is not a part of the graph, it's more of a feature of the graph, a feature of the function. It helps us sort of hang the function on the grid. We can draw the function getting closer and closer and closer to that line as indicated here. I want to emphasize that when we say the line x equals minus 3, we're not talking about a number x equals 3, but a line x equals 3. The line whose equation is x equals minus 3. The graph of x equals minus 3 would be the set of all points xy on the plane that satisfy this equation. And if you think about that, the set of all points xy that satisfy the equation x equals minus 3 would be the set of points minus 3 comma y. The set of all the points on this vertical line. Y could take on any value, but x is fixed at minus 3. So when we talk about a vertical asymptote, it's an actual line. We say x equals minus 3, meaning we're talking about the equation x equals minus 3, whose graph is a vertical line. We will sometimes say the vertical asymptote happens at the number x equals minus 3, but the vertical asymptote is the line whose equation is x equals minus 3. We have another vertical asymptote here, It's the line x equals 2. So this vertical line is the graph of the equation x equals 2. It's the set of all points xy on the plane that satisfy the equation x equals 2. So that would be these points where x is 2, but y could take on any value. It's a vertical line. So our definitions are, if you ever have the limit as x approaches c, f of x is equal to either plus or minus infinity, or maybe the limit as x approaches c from the right of f of x is plus or minus infinity, or the limit as x approaches c from the left of f of x equals plus or minus infinity, which are situations that we have here or here, then the line whose equation is x equals c is called a vertical asymptote for f. So we'll see lots of examples in this class of functions that have vertical asymptotes, and the term vertical asymptote will become an integral part of our vocabulary in calculus. Not every function will have a vertical asymptote, but many of them do, and when a function does have a vertical asymptote, it's an important feature of that function. It tells you how that function is behaving at c. We'll look at some instructive examples on this slide. First of all, think about the graph of y equals 1 over x squared. You can see here from your knowledge of this function that the limit as x approaches 0 of 1 over x squared equals infinity. As x gets smaller and smaller, x squared is getting smaller and smaller, so its reciprocal is getting bigger and bigger and bigger. Positive infinity. If you look at the graph of y equals 1 over x, in this case the limit as x approaches 0 from the left of 1 over x is negative infinity, but the limit as x approaches 0 from the right of 1 over x is positive infinity. So x goes to 0 from the right, f of x goes to positive infinity. For another example, think about the graph of tangent x. It's drawn here. And let's look at the limit as x approaches pi over 2 from the left of tangent x. So here's pi over 2. As x goes to pi over 2 from the left, you can see tangent x is going to positive infinity. So the line x equals pi over 2 is a vertical asymptote. But I want to write this in a special way that's going to fit the pattern of the other examples that we've seen on this page. Tangent of x is sine of x over cosine x. So we're talking about the limit as x approaches pi over 2 from the left of sine x over cosine x. And if you look at this, as x goes to pi over 2, sine of x is approaching sine of pi over 2, which is positive 1. Cosine of x is approaching cosine of pi over 2, which is 0. So we have a number on top that's getting closer and closer to 1, and a number on the bottom that's shrinking to 0. So a number that's really close to 1 divided by a number that's really close to 0 is a really big number. And the smaller the number on the bottom gets, the bigger and bigger that number gets. So this limit equals positive infinity. So there's a pattern that's happening on this slide that's pretty typical. In each case, we have the limit as x approaches some number of a quotient where the numerator is non-zero or approaching a non-zero number, and the denominator is approaching 0, and we're getting either positive or negative infinity. This situation is typical for infinite limits. It's a typical situation. You typically have the limit as x approaches c from either the right or the left, I'll say right here, of f of x divided by g of x. F of x divided by g of x. Like think of this one as a constant function. That's your f of x, and here's your g of x. Or your f of x, and here's your g of x. And in an infinite limit, the typical situation is that the numerator, f of x, is approaching a finite non-zero value. It's not zero, it's approaching a finite non-zero value. Or perhaps it equals a finite non-zero value, like a 1 here or here. Or maybe it's approaching a finite non-zero value, like sine of x is approaching 1 here. And on the bottom, the g of x, the denominator, is approaching 0. Whenever you have that situation, this quotient is going to be getting bigger and bigger and bigger the closer and closer x gets to c. Because the top is approaching a finite non-zero number, and the bottom is approaching 0, so that quotient is getting bigger and bigger and bigger, the smaller and smaller that denominator is. The smaller and smaller g of x is, the more and more times it's going to go into this finite number, f of x. So this quotient gets bigger and bigger. So you're going to get either plus or minus infinity, and that sign, positive or negative, it's really going to depend on the signs at the top and bottom, whether they are positive or negative. So as we go through today's lecture, this typical situation is going to pop up time and time again. It's going to be the key to evaluating most infinite limits. Not all, but most. Let's look at an example of this typical situation. Let's investigate the limit as x approaches 3 of 7 minus x divided by x minus 3. You can see here that as x goes to 3, x minus 3 is approaching 0, and 7 minus x is approaching 4. So we are in this typical situation from the previous slide. So we're expecting to get positive or minus infinity for this limit. And because of that, because of the fact that we're getting 4 divided by 0, which looks like positive or minus infinity, let's investigate the right-hand and the left-hand limits separately. Let's first of all think about the limit as x approaches 3 from the left of 7 minus x divided by x minus 3. So on the top, as x approaches 3, 7 minus x is getting closer and closer to 4, which is definitely a positive number. But what about the bottom? As x approaches 3 from the left, x minus 3 is getting closer and closer to 0. So it's approaching 0. But let's investigate the sign, whether it's positive or negative as it approaches 0. And I find it helpful to draw a number line as a visual aid to analyze what's happening here. In this limit, we have the limit as x goes to 3 from the left. So x is to the left of 3, getting closer and closer to 3. So this x minus 3 is going to be a negative number. I mean, think about x, maybe x is 2.9. It's just to the left of 3. 2.9 minus 3 is going to be negative. So although the x minus 3 is approaching 0, it's negative as long as x is to the left of 3. So in this situation, the numerator is approaching a positive number 4, while the denominator is shrinking to 0, but it's always negative. So you're getting a positive divided by a negative, which is a negative, and because the denominator is turning into 0, you're getting negative infinity. So this is typically how you work out an infinite limit. Let's try the limit as x goes to 3 from the right of 7 minus x over x minus 3. Again, the top, 7 minus x, approaches 4, which is a positive number. But let's analyze the denominator. X is approaching 3 from the right. So this is definitely approaching 0. It's approaching 3 minus 3. But is it positive or negative? Well, let's jump back to our number line. X is approaching 3 from the right here. So x, think of it as like 3.1 or 3.01 or something like that. X minus 3 is going to be positive because x is just a little bit bigger than 3, so x minus 3 is a positive number. So this x minus 3 that approaches 0 is a positive number. So in this situation, the numerator is positive, the denominator is a positive, but it's getting closer and closer and closer to 0. So the quotient becomes bigger and bigger and bigger. It approaches positive infinity. The smaller and smaller x minus 3 gets, smaller and smaller positive number, the more and more times that number is going to go into this numerator, which is very close to 4. So you're getting a bigger and bigger and bigger quotient. So the left-hand limit and the right-hand limits here didn't agree. We had negative infinity and we had positive infinity in the other case. So we would have to say the limit as x approaches 3 of 7 minus x divided by x minus 3 does not exist. Although the individual left and right-hand limits made sense, and we got two versions of infinity for them. Just for the sake of completeness, I've graphed the equation y equals 7 minus x over x minus 3 with the graphing utility, and here it is. Here's the way it looks. You can see that this must be the point 7 right there because that's the x-intercept. And to get y equals 0, you'd have to have 7 minus 7. X would have to be 7. And you'll see here that we have a vertical asymptote right at x equals 3. So the line x equals 3 is a vertical asymptote. And sure enough, you can see that as x goes to 3 from the right, f of x is going to positive infinity. And as x approaches 3 from the left, f of x is going to negative infinity, as we already knew. In this next example, let's investigate the limit as x approaches 0 of 1 over 1 minus cosine x. When you look at this limit, the numerator is 1. On the bottom, we have 1 minus cosine x, and x is approaching 0. So 1 minus cosine x is getting closer and closer to 1 minus cosine 0, or 1 minus 1. Cosine 0 is 1. So what we're getting is 1 divided by 1 minus 1, or 1 over 0. So we're in this typical situation that we mentioned before. The denominator is approaching 0, the numerator is approaching a finite number, or in fact already is a finite number. So we're expected to get either plus or minus infinity for this limit. And because of that, let's investigate the right-hand limits and left-hand limits separately with the anticipation that maybe we're going to get positive infinity for one and negative infinity for the other. We'll do it separately. Starting with the limit as x approaches 0 from the left of 1 over 1 minus cosine x. The top is positive, but the bottom, as we said before, is getting closer and closer to 0. It's getting closer and closer to 1 minus cosine 0, or 1 minus 1. But is it positive or negative? Right now we can see we have a positive number divided by a number that's getting closer and closer to 0, so the result is either going to be plus or minus infinity. So the key is whether this 1 minus cosine of x is positive or negative. Let's analyze that. The x is plugged into cosine, so we know to interpret the x as a radian measure. So we're on the unit circle. And x is approaching 0 from the left, so it's approaching the radian measure 0 from the left, meaning x is a negative radian measure. So it's negative, getting closer and closer to 0, as in this picture. And cosine of that x is a number that's the x-coordinate of this point at x radians. And that's slightly less than 1, as you can see from this picture, or that you already knew from your knowledge of cosine. So you have 1 minus a number slightly less than 1, and that's positive. Very close to 0, but positive. So here we have a positive number 1 divided by a positive number getting closer and closer to 0. So that quotient is going to be positive infinity. Let's look at the limit as x approaches 0 from the right of 1 over 1 minus cosine x. Again, the numerator is positive. The denominator approaches 0, but is it positive or negative? Well, that radian measure x is now approaching 0 from the right, so it's positive, a positive radian measure, getting smaller and smaller and smaller, closer and closer to 0. And cosine of that, again, is a number, positive number that's slightly less than 1. So 1 minus cosine x is going to be positive. So here we have a positive number divided by a positive number getting closer and closer to 0. And again, the answer is going to be infinity. So whether x approaches 0 from the left or the right, we get infinity. So we can say that the limit as x approaches 0 of 1 over 1 minus cosine x equals infinity. That's our answer. And here's the function drawn with the graphing utility. I've graphed y equals 1 over 1 minus cosine of x, and you can see here clearly as x gets closer and closer to 0, f of x is getting really big, really fast. The limit as x goes to 0 of 1 over 1 minus cosine x equals infinity. I'll summarize all of this with the rule of thumb. You'll find yourself using this rule of thumb quite often in this course, and it applies not just to the infinite limits that we've talked about today, but all limits that have the form limit as x approaches c, f of x over g of x. The limit as x approaches c of a quotient. Here is how you should evaluate such a limit. There are basically 3 different scenarios that can happen. And in one of those 3 scenarios, you'll be in the infinite limits situation of today, but in the other scenarios, you'll be in a situation that you've learned how to deal with in previous lectures. The key is this. Look at the denominator g of x in this limit. If it happens that the limit as x approaches c of g of x is not 0, that's the best situation of all. In that case, you can just use a plain old limit law. The limit as x approaches c, f of x over g of x equals the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. And provided these 2 limits exist, you'll get an answer. The top number divided by the bottom number, which is not 0. So that's going to make sense. So that's the best situation. Secondly, it might work like this. Imagine the limit as x approaches c of g of x equals 0 this time. If it's not equal to 0, you're in good shape. But imagine the limit as x approaches c of g of x equals 0. And let's say it just happens that the limit as x approaches c of f of x is not equal to 0. It's some non-zero number. In this case, you are in exactly the situation that we were in today. This is the situation that gives you an infinite limit. The top is turning into a non-zero number. the bottom is shrinking to 0, you're going to get positive or minus infinity. And maybe plus infinity from the left or negative infinity from the right or vice versa. The point is, this limit, it may not exist. And in fact, if it's equal to infinity, technically it doesn't exist. However, it, or maybe its right or left-hand limits, could be plus or minus infinity. So what you'll want to do in this situation is apply today's techniques. So situation B is handled the way we handled things today. You've learned how to tackle situation B. Now finally, we could be in situation C. The only remaining case would be where the limit as x approaches c of g of x equals 0, as it was here, but this time the limit as x approaches c of f of x actually equals 0. Now, what's happening here in the limit as x approaches c of f of x over g of x? You're getting 0 divided by 0. And that's completely ambiguous. 0 divided by 0 doesn't make any sense. Well, how do you handle that? Think about what we did a few lectures ago. This is a situation where we would have applied an algebraic technique to try to get rid of that 0 denominator. So whenever you get 0 over 0, try to algebraically cancel to arrive at one of the forms A or B above. A, you'll get a finite number for your limit. B, you'll get plus or minus infinity. So if you think about what we did previously in previous lectures when we had the form 0 over 0, we algebraically reduced until we got into situation A. And then we got an actual number for our limit. We didn't see it happening then, but it could happen that you could land in situation B, where after you've algebraically reduced, you get a situation where the limit as x approaches c of g of x is 0, and the limit as x approaches c of f of x is not equal to 0. In that case, you'll get plus or minus infinity. And we'll look at an example on the next slide where both of these situations, A and B, happen after an algebraic reduction. But to conclude our summary, I should also remind you how to find the vertical asymptotes whenever you have a function that has the form f of x over g of x. From what we've seen today, we know that those tend to happen where the g of x is equal to 0. So the first step in finding your vertical asymptotes is to solve the equation g of x equals 0. Those solutions, let's call them C, the values of C that make g of x equal to 0, those solutions C are then candidates for vertical asymptotes, but it doesn't mean you have a vertical asymptote. Remember, to have a vertical asymptote, the limit as x approaches c has to be positive or negative infinity. So you've got to check. For each such c, check to see if the limit as x approaches c from either the right or the left of f of x over g of x equals positive or minus infinity. And if it does, the line x equals c is a vertical asymptote. So on this page is a summary of everything we've talked about today and an indication of how it links back to things that we've talked about previously. Let's do a final example. Here we want to locate the vertical asymptotes of the function h of x equals x to the fourth minus x cubed plus x squared minus x divided by x cubed minus 3x squared plus 2x. If you think about our procedure from the previous page, the first step in finding your vertical asymptotes when you have a function that's one function divided by another one, as we do here, is to look at the values that make the denominator equal to 0. Set the denominator equal to 0 and solve. And to do that, we could just, in this case at least, factor the denominator. Let's see, an x comes out first. We get x times x squared minus 3x plus 2. And now that quadratic, x squared minus 3x plus 2, factors as x minus 1 times x minus 2. So we can see plainly here that the values of x that make the denominator equal to 0 are x equals 0, x equals 1, and x equals 2. So those are our candidates for vertical asymptotes, x equals 0, 2, and 1. But these are only the candidates. We don't know we have vertical asymptotes yet. But we now know where to look at x equals 0, x equals 2, or x equals 1. And we have to check those individually. Check the limit as x approaches 0, for instance, of h of x, and see if we get infinity or negative infinity. So before we check, let's look and see if we could simplify h of x a little bit. You can factor an x out of the top here, and then the x cubed minus x squared plus x minus 1. That factors as well. You can FOIL this back to check. It factors as x squared plus 1 divided by x minus 1. Just FOIL that out quickly in your head, and you'll get what we have here. And you'll see some cancellation. An x over an x, those cancel. And an x minus 1 on top and an x minus 1 on the bottom, those cancel. And so we get x squared plus 1 over x minus 2. Now I should be quick to point out that this cancellation, or these cancellations, only work if x is not 0. So you don't have 0 divided by 0 here. Remember, you want x divided by x equals 1. 0 divided by 0 is not 1. And also you can't have x equals 1 because otherwise you'd have 0 divided by 0 here. So just as a reminder, h of x equals this expression provided x is not equal to 0 or 1. Now, 0 and 1, you can't even plug them into h because you're getting a 0 on the bottom here for h. So, okay, let's check now these three numbers individually to see if we have an asymptote. Let's start with checking x equals 0. So we would look at the limit as x approaches 0 of h of x. Now here, x is approaching 0, so it's not equal to 0, it's just getting closer and closer to 0, so it's not 0. And also if it's getting really close to 0, it's not 1 either. So x is equal to neither 0 nor 1 in this limit. So our h of x that occurs here actually equals this quotient, x squared plus 1 divided by x minus 2. So our limit is the limit as x approaches 0 of x squared plus 1 over x minus 2. Now if you look at this limit, you're in situation A from the previous page. The denominator is not turning into 0. You could just plug in x equals 0, you get negative 2 for your denominator. In fact, this is a rational function. To evaluate this limit, just plug in x equals 0, and you get negative 1/2. Now, that's not plus or minus infinity. So all this means is there's no vertical asymptote here. There's no vertical asymptote at x equals 0, even though 0 made the denominator 0. You didn't get plus or minus infinity in this limit, so no vertical asymptote. Let's check x equals 1. So we would look at the limit as x approaches 1 of h of x. Let's see. Now again, x is not equal to 1, and it's close to 1 since it's approaching 1, so it's not 0. So this h of x is the limit as x approaches 1 of x squared plus 1 over x minus 2. And again, here you can just plug in 1 to this rational function. The denominator is not turning into 0, and you get negative 2. And that's not plus or minus infinity, so there's no vertical asymptote here. So finally, we need to check x equals 2. So for x equals 2, we're looking at, let's see, h of x is going to be this. Oh, look at this. As x gets closer and closer to 2, the denominator here is turning into 0, but the numerator is turning into 2 squared plus 1. It's turning into 5. So we're in a situation here where the numerator is approaching a positive number, and the denominator is approaching 0. So it looks like here we might actually get plus or minus infinity. And in anticipation of that, let's let x approach a 2 from the right, because you might get either plus or minus infinity depending on whether you're going from the right or the left. So we'll simplify things just by looking at the right. And h of x simplifies to this expression. So we have the limit as x approaches 2 from the right of x squared plus 1 over x minus 2. Well, the x squared plus 1 is approaching 5. The x minus 2 on the bottom is approaching 0, but x is just a little bit bigger than 2, approaching 2 from the right. So x minus 2 is going to be positive. So we have a number close to 5 divided by a number that's getting closer and closer to 0, and it's positive. So that's positive infinity. So finally, in this third try, we got a situation where we have a vertical asymptote because we got infinity as x approached 2. That means the line x equals 2 is a vertical asymptote. So that solves this problem, this example, and indicates some ways that these limits can play out. Just to complete this, I've graphed the function y equals x to the fourth minus x cubed plus x squared minus x divided by x cubed minus 3x squared plus 2x, the function we started with, here with the graphing utility. And you can certainly see that you have a vertical asymptote at x equals 2. And as x approaches 2 from the right, f of x goes to positive infinity. You'll see here, as x approaches 2 from the left, f of x goes to negative infinity. And also note that this graph has holes in it at x equals 0 and also x equals 1, there and there, because you can plug neither 0 nor 1 into this function, h of x. If you plug in 0, you're dividing by 0. So the hole in the graph right there, there's no point on the graph. And at the same time, if you try to plug in 1, you're also going to be dividing by 0. So there's a hole in the graph at x equals 1. So it's a kind of interesting graph. I want to issue one word of caution. Not all vertical asymptotes result from a 0 denominator. That's the way it's been working previously today, but that's not always going to be a situation that's not every time you get a vertical asymptote will you have a 0 denominator. For example, think about the graph of y equals ln of x. In this graph, as x approaches 0 from the right, ln of x goes to negative infinity. So that means that the line x equals 0, or in other words, the y-axis, is a vertical asymptote. The y-axis is a vertical asymptote of ln of x. But here you have a function that's not a quotient. So be alert to that, although you have this typical situation that we talked about earlier today with infinite limits arising from a function that's having the form f of x over g of x. It's not always going to happen. So the important thing is here, you need to know your functions, know your basic functions really well in order to analyze them. As always, it's important to work some exercises Even if everything in lecture seemed perfectly obvious and made sense, you never know whether you understand this or not until you work exercises yourself. So work them. Next time, we'll look at limits that have the form limit as x goes to infinity, f of x equals L, where x is approaching infinity, but f of x is approaching a finite number L. Those are called limits at infinity. So I hope to see you then, and goodbye.